Is the screen visible? Okay. Okay. Got it. Now in the last period, we have seen multi-rate signal processing. Under that, what is the meaning of multi-rate signal processing? Then what is decimation? What is interpolation? And how it is to be performed by a decimation factor of d equal to 2 or d equal to 3. We have solved examples also. You are inserting 3 minus, you are removing the samples in this case. In the upsampling, you are inserting zeros, right? And also, we have seen frequency domain analysis of upsampler, and we concluded that there are multiple images in the spectrum of upsampler. That's why it is necessary to use anti-imaging low pass filter, bandwidth of pi by I, right? In the interpolator. In the decimator, we have to use again a low pass filter, but it is not anti-imaging, it is anti-aliasing filter. Next, after this slide, I will show you the how it is actually happening, right? So right now you should know that anti-imaging filter is used in, upsampler or interpolator, while anti-aliasing filter is used in decimator, and that anti-aliasing filter is to be used prior to decimator, while this anti-imaging filter is used after the interpolator. So now this also example we have solved, interpolation by a factor of I equal to 2, I equal to 3, etc. And mathematically also how to do it, n by I, like that, and how to draw this, right? This is just in, I am revising what we have done last time, right? Because it is a gap of, I think, more than 8 days, right? And in the frequency domain analysis, we have seen yz equal to x z raised to I. This also we have derived everything. And I asked you to derive similar way for decimator. And in the decimator, you will find that I x z by d. Here is z raised to I is there. So that should be kept in mind, right? Now, by in the how is the spectrum? You take the Fourier transform. In the Fourier transform, simply replace z by e to the power j omega, right? So now this should be kept in mind. See here, up to this we have already covered. X of n interpolated, we get y of n x n by I, right? And in the frequency domain, x e to the power j omega, you get x e to the power j omega into I, like this, right? Or in the z domain, it is z raised to I, yz equal to x z raised to I. So you should know this. After interpolator, what happens in the z domain or in the frequency domain, right? It is useful in case of MCQ as well as in theory also, right? Frequency domain analysis of decimator as well as interpolator. This is about upsampler. In the downsampler, Z divided by, yes, D. Now, this concept of anti-imaging filter also we have seen last time, right? So what is the need? Because we are getting multiple images or multiple spectrum. That's why it is necessary to use anti-imaging filter H of N, which is a low pass filter with a bandwidth of pi by I. In the interpolator or in the decimator, it is required to use, yes, always it should be with the one filter, low pass filter. Here it is anti-imaging filter. In a decimator it is anti-aliasing filter, and it should be connected prior to downsampler. This should be noted, right? This will help you in MCQ as well as in theory paper. Now I think your test examination is starting from 23rd, right? If you refer the website, sample papers are available. Sample papers, again I am telling, right? It is not question bank. That should be kept in the mind. Now this is the function of anti-imaging filter to avoid the multiple images in the output spectrum, right? Now let us see. Up till now we have seen interpolator and decimator separately. But there are some cases, or most of the times, you will find that sampling rate conversion may require by a fractional number, rational number, by a rational number. And we have seen that by using interpolator or by decimator, what we do? We should have integer number only, right? Interpolation by I equal to 2, 3, 4 means 4 minus 1, 3 zeros you will be inserting, or I can be 5, or D also can be 2, 3, 4, 5 and so on. But I and D, in both the cases, it should be an integer number or integer factor. So now this is the new topic. Write down: in decimation and interpolation, the sampling rate conversion is done by integer factor, where D and I are integers. Now, but when it is not necessary that always it will satisfy your need, because in the first lecture, introductory lecture, we have talked about whenever you have the devices with multiple sampling rates, right? Like I have also given you example of speech signal and music signal, right? And you are transmitting through the same channel, both the signals. That time sampling rate conversion has to be done. So how you are going to do it again? By using I or D. If you want to increase the sampling rate, use interpolator. If you want to decrease the sampling rate, use decimator. In both the cases, they should be integer, but it is not necessary that this will satisfy always your devices. Yesterday, in the previous class, we have seen CD and other devices, tapes, right? Both have different bit rates, right? Sampling rate is they are using differently. So now what is the solution on that? If you require sampling rate by a rational factor, then you write down the steps. The sampling rate conversion by a factor I by D involves the following steps. First is perform interpolator by a factor of I. Now filter the output. See, in the practically whenever you are using interpolator or decimator, it should be associated always with filter. right? It has to be associated with the filter. Now, in case of this is actually practically filter the output of interpolator using a low pass filter anti-imaging filter with a bandwidth of pi by I. Write down pi divided by I. Why do you need this filter? Right? To avoid this multiple images, you are using this filter in the interpolator, right? Now, the second step, write down third step. This can be asked again. I am asking you. This is a question in case of short note in the descriptive paper. Sampling rate conversion by a factor of I by D. You have to draw the block diagram and frequency analysis too, right? So now, and the what is the next step? The output of anti-imaging filter is passed through the another low pass filter, which is called as anti-aliasing filter. This anti-aliasing filter is always associated with a decimator, right? So this should be kept in the mind. Whenever you are using decimator, practically it should be always associated with a anti-aliasing filter, right? Now, and this should be connected prior to the decimator, and this is connected after the interpolator. This is prior to decimator to avoid aliasing effect due to decimator, right? So now finally the signal band limited to pi by D is decimated by a factor of D. These are all four steps which are used to convert sampling rate by a rational factor I by D. Right? You may be given a factor, suppose 1.4. Then how you are going to do it? That you have to write down. Right? So now everyone to draw the block diagram. Then instead of using two filters, one is anti-imaging and another is anti-aliasing, can we combine both? Yes, it is possible to combine both. You design another low pass filter HI, right? So which is the cascade of these two, because you are cascading this filter convolution of this filter should get you this filter, right? Whenever both are connected in the cascade, how to get the equivalent low pass equivalent filter is convolution of this filter with convolution of another filter, and you can replace entire cascade of these two by a single filter HL, right? Which will perform the task of cascade of these two. And you have XN interpolator by a factor of I, right? You get some output. That output is to be passed through a low pass filter, which is cascading convolution of this filter and this impulse response, right? Then after the low pass filtering, pass through the decimator, which is downsampling by a factor of D to get Ym. It is the same as that of this Ym, right? So these are all the four steps which are to be used for sampling rate conversion by a rational factor I by D. Is this clear? Is it okay? Yes? So write down, draw the block diagram and write down everything. The process of sampling rate conversion by a factor of I by D is shown. Here it is important to note in order to preserve the spectral characteristic of Xn, the interpolation has to be performed first and decimation has to be performed next. See, in objective question they can ask you which is to be performed first. So you should know interpolation has to be performed first and then you can perform decimation, right? So that why do we require this? To preserve the spectral characteristic of Xn. Again they can ask you why, what is the requirement of, why do we want to do this? So the need is to preserve spectral characteristic or frequency response of x of n, right? Now, the two low pass filters with bandwidth of pi by I and pi by d can be combined to a single low pass filter with bandwidth minimum among pi by I comma pi by d. Yes, they will serve the same purpose. You can have a single filter which is having a bandwidth if you want to avoid this convolution, because again processor has to be used, right? So if you want to avoid this convolution, what is another way? Another way is you can, because both are low pass filter, you can use the low pass filter for which the bandwidth is minimum for pi by I and pi by d, right? If its bandwidth is 1 kilohertz, its bandwidth is 2 kilohertz, then this 1 kilohertz pi by I can be used, only one, right? So now go for the next one. What is the now? We have studied interpolator, we have studied decimator, and in both the cases, in the time domain analysis as well as we have to do frequency domain analysis. Now in the frequency domain analysis, let us see what is the effect. Everyone to note down the block diagram. Sampling rate conversion by a factor of I by D in the frequency domain analysis. You take Fourier transform of input, Fourier transform of output, again Fourier transform, like this. Draw this, all of you. Yes, done. Noted. Now, in the frequency domain, you take the Fourier transform. Now, let us see in the time domain, if input is x of n, how to get this V output? It is x n by I, right? Then you have, yes, WL, band limited version of WVL, because we have to pass this through a low pass filter to preserve the spectral characteristic of x of n, right? Then you get another signal, that is WL, right? Now this WL, then YM is the decimated version of WL. How to get this decimated version of WL? By WD into L. Either you can write XN or M or L, whatever you want to write, you can write down, or K, it does not matter, right? So now you are getting WD into L, which is the output YM, right? This is the answer. Now let us see what happens if you take the frequency Fourier transform of input, then output. All these are all the spectrums, right? So spectrum of a signal means you are taking Fourier transform and you represent by capital X e to the power j omega, or simply capital X omega. So always whenever you are representing in the frequency domain, write down capital X, right? Either x omega or x e to the power j omega, right? Now let us see step by step what is the effect, right? We have seen that V e to the power j omega, that is, which is this is we have already derived, right? It is e to the power j omega into I, or we have written z into z raised to I, and z is replaced by e to the power j omega. Is it okay? Are you getting? Are you getting? Yes. Is this fine? It is in continuation with the last lecture, what we have derived. What is the effect in frequency domain? Right? We have seen that for the interpolator in the frequency domain, if input is x of z, yz output is, yes, z raised to I. Simply replace z by z raised to I. Or if you take the Fourier transform, e to the power j omega is replaced by e to the power j omega into I. Right? That is because of interpolator. Effect of interpolator in the frequency domain. Derivation we have seen last time. Now, HL is the impulse response of the low pass filter. H omega is the frequency response of a low pass filter. Take simple Fourier transform of H of L. Right? H of L is in time domain. See, small letters. Small letter means time domain. Capital letters in frequency domain. Now, the low pass filter is designed to have the cutoff frequency of, say, WC, which is minimum of pi by I, comma pi by D. Why it should be minimum? Because we know that low pass filter is required in both the cases, in interpolator as well as in decimator. In interpolator, it should be after interpolator pi by I bandwidth. In the decimator, its bandwidth should be pi by D anti-aliasing filter, and it should be prior to decimator. So now whenever we are combining these two, take the minimum bandwidth, right? Minimum cutoff frequency. Automatically it will satisfy both the conditions, right? Now see, minimum of pi by I comma pi by D, right? That should be the cutoff frequency of the filter, which will solve the problem of anti-aliasing as well as yes, anti-aliasing as well as anti-imaging filter, right? Now, what about the spectrum of the output? Here we have passed through this. So what will be the effect? Whenever in the frequency spectrum, whenever you are passing through the filter, is spectrum is here in the time domain there is a convolution. In the frequency domain it is a multiplication. Multiplication of V omega H omega will give you W omega. Are you getting? Yes? Is it okay? Is this understood? My question is this understood? Yes? Shall I proceed? Okay. Okay. So now, see again, this can be an MCQ question. You will be given bandwidth of this and this. How to select the bandwidth of the I by D, which is the low pass filter, right? Now, see here, the spectrum W e to the power j omega is H e to the power j omega into V e to the power j omega. Multiplication. Convolution is converted into multiplication, right? And similarly, we can write in this way. It is a low pass filter, right? Because x e to the power j omega is I times V e to the power j omega. So we have here it is written I into this one, right? Now what about y e to the power j omega? Y e to the power j omega is decimeter by a factor of integer factor d. The spectrum of the output signal of a decimeter is given by, it is 1 by d, k equal to 0 to d minus I, w e to the power j, w minus 2 pi k divided by d. Now how to get this? See, like the interpolator we have solved. Now this we have to solve for decimeter. See here. Up till now we have come. Now go into the decimeter. Here in interpolator we have seen what is the effect. In the decimeter also what is the effect, right? So now write down this. Since there is no aliasing in the output, the equation can be evaluated at for k equal to 0 alone. So y e to the power j, that is output spectrum equal to w e raised to e to the power j omega divided by d. There it was in the interpolator j omega into I was there. Now here it is j omega divided by d is there, right? So now final answer is I by d x e to the power j omega I divided by d. So this is the final answer. This is the effect on spectrum. I hope you understood. This is the effect on spectrum. Where Wy This is 0 to wy. Wy is the minimum of pi by d by I comma pi. Right? This is the equation is the spectrum of sampling rate conversion by a factor of I by d. So this is for 8 marks in theory paper, and in the MCQ there are a number of 3, 4, 5 questions I have already discussed. Right? Now next, write down all of you multi-stage implementation of sampling rate conversion. Write down the next topic, and one more last topic is remaining, that if possible we'll cover today, or in the one more lecture we'll be getting. Right? So now write down multi-stage implementation of sampling rate conversion. In the sampling rate conversion, when the sampling rate conversion factor I or D is very large, right, then the multi-stage sampling rate conversion will be computationally efficient whenever you are realizing the interpolator or decimeter. When we are, this also can be a question, when to go for multi-stage implementation, right? Whenever, yes, what is the answer? When the sampling rate conversion factor I or D is very large, right? Then you can use multi-stage sampling rate conversion for realization. Now, what is this? In interpolation, if the sampling rate factor I is very large, then the I can be expressed as, yes, it is the product of positive integers like this. Similarly, we can do for D, right? This is capital I equal to I1 into I2 into I3 into IL, and so on, right? Now the interpolation by sampling rate multiplication factor I1 comma I2 are implemented separately. Then overall interpolation is obtained by cascading L stages of interpolation. So everyone to note down this. What is multi-stage interpolation and how it is achieved? Now write down few answers. Write down answer. Where do we require anti-aliasing filter? And why? Write down answers, all of you. This is question number 1. Question number second is write 4 steps of sampling rate conversion. By I by D. Factor. Next question. What is the effect on spectrum? In interpolator and decimeter. Right equation. Write down all the 3 questions, answers of 3 questions, and then you can exit. All the students. Write down answers and exit. Write down all of you. 3 questions you have to answer. Yes? Not a single question you answered. Okay, Sandhya. Perform okay, okay. Second question. Perform interpolation, okay. Filter the output by a low pass filter. Right, right, right. ठीक है. First question is remaining. See, anti-aliasing filter, we are talking in terms of now, yes, here in the multi-rate signal processing. In the multi-rate signal processing, we require anti-aliasing filter at the input side of decimator to avoid aliasing effect at the input of a decimator, right? Like last time we have seen anti-imaging filter, yes, decimator. Okay, Devashri, right. Yes. Answer all the 4 questions and then you can exit.